We're going to start doing some more circular motion problems or rotation problems. Mr. Lane was a math teacher at Big Bend until recently. He had a Volkswagen EOS. I don't know how you pronounce that thing. Anyway, but one day when we were going to be studying this, I went out with a meter stick and measured the diameter of one of the wheels. So we want to determine the centripetal acceleration of a point on the outer edge of the tire when the car it is on is traveling at 71.8 miles per hour. And we'll want to determine it in meters per second squared. So we haven't studied rolling motion yet. We'll do that later in the quarter. Let's just imagine a point that's maybe on the wheel, right here at the bottom of it at some instant in time. We'll imagine that the wheel is rotating in this direction, and so the center of the wheel is moving to the right at 71.8 miles per hour. Now, in one rotation, and let's just suppose that one rotation occurs, this point of the wheel is now over here. The distance that the wheel will have moved is going to be 2 times pi times the radius of the wheel, or pi times the diameter of the wheel. The speed at which the wheel is moving to the right, just v with no arrow on it, is going to equal 2 times pi times r divided by a capital T. T is the period of one rotation. We know what this speed happens to be. It's 71.8 miles per hour. Those are inconvenient units. Let's convert those. And I'm going to remember that 1 mile is 1,609 meters. This is something that I give you when you take tests, by the way. And then 1 hour is 3,600 seconds, and that speed happens to be 32.1 meters per second. Well, we already have enough information to figure out what the centripetal acceleration happens to be. The acceleration is equal to v squared over r, and so that's the speed we squared. The only thing we have to worry about is the radius. The wheel diameter is 62.0 centimeters. The radius would be half of that, or 31.0 centimeters, which is 0.310 meters. And if you're a little sketchy on accepting that, do this. 31.0 centimeters times 1 meter over 100 centimeters, and you'll get the correct result. This is a safer way to do that. This is a definition. 100 centimeters is by definition exactly 1 meter, so one of those infinite number of sig figs on that thing. So you'd get 0.310 meters. Okay, so let's just plug in the numbers here and calculate. And when I do that, I get 3.32 times 10 to the third meters per second squared for that acceleration. That's the acceleration in meters per second squared. If we try to figure out how many g's it is, here's the idea that we do when we do that. We think of the acceleration as equaling some number times the acceleration due to gravity. Well, we know what a is. We know what the acceleration due to gravity. That some number, by the way, that's the way I draw the Greek letter alpha. It's not the greatest. 3.32 times 10 to the third meters per second squared divided by 9.81 meters per second squared. And when we do that, we get that alpha is equal to about 339. So you could say that the acceleration is 339 g's. Something we're going to address when we get to relative motion. Because the wheel is rolling, that point on the wheel is not just traveling in a circle, it's also going to the right. And the actual motion of that wheel in space ends up doing something like this, where it's got this really weird motion. In the relative motion chapter, I'll show that the motion sideways at constant speed doesn't affect the acceleration of that point, and that it is centripetal acceleration that's producing the acceleration here. Let's do another one. A favorite Carnival ride that goes by all sorts of different names is one where you go into this kind of circular room. Not really a room, it doesn't have a roof on it or anything, but it has a diameter of, I just made up a diameter. And occupants stand on the horizontal floor against a vertical wall while the ride spins. How many RPM must the ride turn for the occupants to feel 1 g of centripetal acceleration? Well, that RPM is revolutions per minute. Let's put that off for now and just figure out, if you're traveling in a circle with a diameter of 8.15 meters, then what will your centripetal acceleration be, or how fast does your speed have to be traveling in that circle in order to feel 1 g of centripetal acceleration? So in this case, we know that the acceleration is 1 g, and it'll be some v squared over r. If we can figure out v, then we can start worrying about that revolutions per minute. So let's see what we get here. Just doing a little algebra. V squared is equal to rg. V is just going to be the square root of that. Square root of 4.08 meters times 9.81 meters per second squared. Underneath that radical, I've got meters times meters per second squared, which will give me meters squared per second squared. But you take the square root and you get meters per second. Then I get the speed has to be 40.0 meters per second squared. Okay, and that's the way I can show three significant figures. Zeros to the right of a decimal point, if they are also to the right of a non-zero number, are significant. Now, that speed is going to equal 2 times pi times r divided by the period of rotation. Okay, how long it takes you to travel one circle. We can work with that and figure out what the period must be, or the reciprocal of the period, I've pointed this out, is 2 pi r times the frequency. And so we can find the frequency. Frequency, that's how many times per second you would complete a rotation, is just going to be 40.0 meters per second. That's what that thing is. Divided by 2 times pi times that radius, which is 4.08 meters. Plug in the numbers here, and you get this would be 2.47 times 10 to the minus 1. I could write that as 0.247 times 10 to the minus 1. It would just be rotations per second. The meters divide out here, and you would have per seconds as the only units, but I'm going to think of that as a rotation per second, or a revolution per second, whatever you want to call it. Well, I want to know how many times it does that per minute, so I just multiply by 60 seconds per minute, and now I've got rotations on top and bottom, rotations on top and minutes on the bottom. That's RPM. And so we get some number, 14.8 RPM. Somewhat unusual units, but we did introduce them a video back or so. All right, that's our first couple of problems here.